Anything you say or do can and will be recorded for evidence. So deflection of trusses. I want this. You guys were driven by your questions. So I guess you've all done the topic. The basic theory, you may have done the topic, or you've attempted the topic. The basic theory is you have a truss, you put a load on it, you work out the load and all the members, and then you work out how much member each member extends, do a bit of geometry, you get a deflection. All happy with that? So we're done here. So we'll do a truss, do a basic truss up on the board. Are you guys comfortable working out, given the load there, working out the forces in all the members? Everyone happy with that?
Yep.
Okay. George, are you happy with that? Yeah, sure. Okay. So if we pick some dimensions, there's a few steps to it. The basic statics will give us the loads here. We know that if we put a load here, say stick a horizontal load there as well, that's going to be a pin, that's a roller. So any horizontal forces are going to be resisted right here, because that can't give us any horizontal resistance. So if I put some dimensions in here and say that's 10 meters, and that's a load of 10 and that's a load of 5, from statics I immediately know that reaction there is going to be 5. And from plain simple geometry, I know that that is going to be 5 there and 5 there as well. Okay. We'll make it a bit more complicated just so we can see an example of one. Do we have an eraser for this board anywhere? Thank you. Alright, so we'll take the 5 load off there. Sorry? Oh, I want the scales, thanks. Okay.
Question, Peter.
Yeah.
A zero force member.
Yep.
So any member that runs perpendicular to that cord, to a cord that has no force off it, a zero force member, is that correct?
So you're talking about that member there and that member there?
Well, say the bottom, so there's nothing at the bottom there. Yep, so nothing there.
Alright, if that's a straight line,
Yep.
then that is a zero force member there. And the reason that's a zero force member is in a pin jointed truss, all these members can only take axial force. Provided you load it at the nodes, which is what I've done, you can't put bending into that thing just by loading at the nodes. And if you can't put bending in there, that's got to be pulling apart, therefore that's always going to be 0. Okay? A little bit later we'll talk about all the assumptions and the 50 million reasons why what I've just said is not true.
And any member going down in the truss,
Yep.
if there's no load on the bottom of it, it's a zero force member then as well?
You can work your way out for various loading conditions. If this load wasn't here, then you can look at that and go, well, that's a straight line, that's a zero force member, that's a zero force member, therefore that's a zero force member.
Yeah.
Okay, but we've just hung a load of 10 kilonewtons on here.
Yep.
So that assumption of what I've just said is not true. The 10 kilonewtons is going to go straight into that. All right. So let's stick a 5 kilonewton there. We've got a 10 meter truss is 10 meters wide. It's say 5 meters tall. Sorry, I'll learn to write more neatly. So we want to figure out what these vertical forces are. Okay? If we take moments about this point here, let's call it A. So the sum of the moments about A equals how much? 0. Okay, the sum about those things, moments is 0. That's because there's no force on there, and if there's any force on there, this is going to be a mechanism. It's not in equilibrium. So the moments about that point there, we're going to have, and that's going to equal 10 times that distance, which is 5. Call that negative because we'll go anti-clockwise positive. And that's that force. We've got this force here, which is our reaction, call it reaction B. So reaction B is going to drive it that way, so plus reaction B times 10, because that's 10 from there. And now we're going to put that force in, so that's going that way, so that's minus 5 times 5. And if I do that, I get minus 50 plus 10 RB minus 25 equals 0. So 10 RB minus 75 equals 0. RB equals 7.5. Please check my maths. I am appalling when I do maths live. Okay. So RB is 7.5. We know that the sum of the vertical loads is all 0. So sum of the forces vertical equals 0. And that means minus 10 plus 7.5. Let's call that reaction A. Plus reaction A equals 0. Minus 10 plus 7.5, we know that reaction A equals 2.5. Okay? Everyone agree on that? Do a quick sanity check on it. The theory that if it looks right, it probably is right. We've got a load pulling that way, so that's going to push down more on that. And there's a load pulling down, so we're going to have 7.5, 2.5. That looks right to me. Okay. The way to check it is you take moments about there, and you sum it all off. Actually, we can do that mentally. Moments about this point is 2.5 times 10 is 25, minus 10 times 5 is 50, minus 5 times 5 is another 25. So that equals 0, correct? Okay. So we've got our reactions now, and now we're going to work out the forces in each member. So the way we do that is we do a cut. If we take that much, so we're going to cut it through there, every bit of this structure is in equilibrium. Okay? So we've got a reaction there of 2.5. And, oh yeah, we've got the horizontal reaction here is 5. And that was just by summing the horizontal reactions. So that's 5. And then we're going to have a force in there and a force in there. So that'll give us two forces. We're going to set ourselves up for simultaneous equations. Let's abandon that one. Let's cut through here instead. Okay. And cutting through there, we know that's a roller joint, so there's no horizontal force. We've got a vertical force of 7.5. We've got a potential force there and a potential force there. And because the horizontal bit of that force has to work out with the horizontal bit of that force. So we know that that's got a vertical component and a horizontal component, yeah? And the vertical component of that has to equal 7.5, yeah? So if I call that force A, this is force A vertical, and this is force A horizontal. That's theta, an angle, and this is force B. So our sum of our forces, sorry, I can't draw that. Sum of our forces vertically are going to equal 0. So 7.5 is going to equal the vertical component of that. Okay, now we have to do a bit of geometry to work out our angle. We had a triangle which is 5 wide, 5 tall, therefore that's 45 degrees. Everyone agree with that? Mm-hmm. Okay, cool. So that's 45 degrees. So the horizontal component is, it's either sine or cosine of that angle. and I always forget which one it is, but you can easily work it out. If it was, in this case, sine and cosine of 45 are the same thing, doesn't matter. If that was a really narrow angle, then the vertical component would be smaller than the horizontal component. So just work out whether it's sine or cosine. So let's call it sine now. Sine 45 degrees times FA is going to equal 7.5. You see that? Everyone agrees so far? Okay. So FA equals 7.5 divided by sine 45, which equals 7.5 divided by 0.707. Can someone put that in their calculator? We should get a number somewhere around 10-ish or so. Sorry?
10.6.
10.6. Okay, so I'm saying that force equals 10.6 kilonewtons. Okay? And that was made up of a vertical force of 7.5, and a horizontal force we know from sheet geometry is also going to be 7.5. Okay, that's just because it's 45 degrees. If that was 30 degrees, that would be different from that, yeah? Okay. So FB, we've got a horizontal component of that one. FB also equals 7.5. Do you want me to go over that again? No? Okay. So we've just worked out the force in this member is 10.6. The force in this member is 7.5. And you can do a series of cuts all the way through the truss to get all the forces. Because that's directly opposite, that's the zero force member, we know that that's also 10.6. Same thing here, we know that that's also 7.5. Or do we? Yeah, because that'll be just the vertical force there. We know that that's going to be 10. And then we have to do a cut through here. Now, remember we had that cut here? We know this is 7.5, so we can put 7.5 there. Okay? So we know that's 7.5. Now we do the sum of the horizontal forces. So that's made up of a horizontal and vertical. Let's call that FC and FD. Sum of the horizontal equals 0. So 5, go minus 5. Actually now we do have to work out whether that's in tension or compression. Because if that's pulling 7.5 that way, that's going to give us a different answer there than if that was 7.5 that way. Okay? So we do have to, this is where you have to be careful with your signs. This is where sign convention is actually not consistent. Tension is normally considered positive, but that's not always the case. So going back to here, we know that that's pulling on that, that's going to be in tension on the bottom. So conceptually I know it's tension. Prove it mathematically. Horrible. To prove it mathematically, we know that that's a force pushing up, therefore that's a force pushing down. That's in compression. Okay, so that's actually facing that way. If that's in compression, then that has to be in tension because there's a force going that way. So that's pulling away from that, that puts that in tension. So I like to label these compression, tension. If that's in tension, that's in tension. That's also compression there. And that will be tension because it's pulling away from that. And that conceptually makes sense because we've got a force pushing up there. We've got this a force pulling down from that joint. And we're going to have a force pushing up on that joint, force pushing up, so it's going to balance that joint as well. Alright, so the 7.5 was in tension. So it is a force pulling away from that joint to the right. And we have this force pulling to the left. So minus 5 plus 7.5 and the horizontal component of that, which we don't know yet, call it FCH, plus FCH equals 0. Yep? Yep. Okay, so FCH is going to be 2.5 kilonewtons. Now we know about the angle, So we know the FC is going to be 2.5 over sine 45, which is, anyone put that in the calculator? 2.5 divided by sine 45?
3.53.
3.53 kilonewtons. All right, that's the force in there. We have to work out whether it's tension or compression. Any takers?
It's positive, it's going to be in tension.
Is it?
Well, that's what, yeah, but it should be negative because 5 plus, minus 5 plus 7.5 is 2.5.
Oh, yeah, that's who stays with
It needs really push this way, doesn't it?
That's true.
So that's going to put that in compression. Okay? Okay.
So, down the bottom, that should be minus 2.5 kilonewtons.
Yes.
Yes.
Okay, so that would be minus 2.5. That will then put that in tension minus that.
Yep.
Yep. Okay. Very good. So just keep a handle on whether you're in tension or compression. Mostly it's easy to tell. Sometimes it's hard. All right. So now we have 3.53 in compression, 7.5 in tension, 3.53 in compression. So a way to check our work would be then to do a cut through here, and cut through there. We have a force there, a force there, a force there. There's our 5 kilonewtons. We know that this is in compression, so this is pushing inwards with 10.6. We know that that's in tension, that's pulling down with 10. We know that that is pushing upwards with 3.53. And if we work out all those, if they balance, it means we've done it right. If they don't balance, you go have your cup of coffee or have chocolate or something and do it again. So there's various equations you can check your work. Is everyone clear on that? Okay. You're confused of it?
No, not at all.
Okay.
I was just doing the maths in my head.
Very
Well,
good.
the
Did
vertical-
does it work?
vertical
I'm a bit scared. Does it work?
Yeah, we've already worked out the vertical components.
Yep.
We had 7.5 and 2.5.
That's right.
Which
So
is
2.5, 7.5.
So it gives you your 10.
Gives us our 5.
That's why, yeah,
Yep.
your vertical components.
So I think we've done it right.
Yeah.
Okay. So there is our truss. There are all the forces in the truss. Okay. We know that our supports, that support does not move. This support does not move vertically, but can go that way if it wants. Okay?
Good question.
Yeah.
So what you've done there is the method of joints.
Yep.
Even though you've broken up, can you do the method of sections through that by doing the moments around any of those points in there?
As in, take the moment about A. Yeah, we can do that. If we cut top off there and do the moment about A.
Yep.
Yeah, we could do that. Do we have to?
No, it's just saying that you can, because
Yes.
as long as it's, you've got to take the point that's not part of the system, that's outside the system.
Yes. Look, you can take moments about any point, theoretically anywhere, and they all equal 0. Everything equals 0 in civil engineering. Okay. If it doesn't equal 0, you're a mechanical engineer. All right. Now, to do deflection, now we look at an individual member. Okay. So let's look at that member. That is a piece of steel tubing, and it's got a force on it of 3.53 kilonewtons in compression. It's going to get shorter. Everyone happy with that? Okay, how much is it going to get shorter by? The change in length is going to equal
So the force times the length
the force times the length divided by the elastic modulus and the area. So if the force gets bigger, you get more change in length. If the length is longer, you get more change in length. The E value, if it's stiffer, you get less change in length. the area is the cross-sectional area of it. If that gets bigger, you get less change in length. So conceptually, you see that makes sense? Then what you've got to do then, once you've got that, is for each member of the truss, work out the change in length. And that will give you values. For example, this will get 5 millimeters longer, 5 millimeters longer, 8 millimeters, 5 millimeters shorter, 5 mil shorter because they have compression, 8 mil longer, 7 mil longer, shorter, shorter. And then with all those adjusted lengths, you redraw the thing and that's your deflection. Please don't make me do that.
Yeah, just out of curiosity, so
Yeah.
we said the area was 200 millimeters.
Yep. Okay.
And it was aluminium.
Okay. So let's say it's aluminium. It is a rod which is 10 mil by 20 mil. Sorry about my writing. Okay. The E value for aluminium, 69,000 megapascals. Yeah, I think that's right. That, by the way, that does vary a little bit depending on what grade of aluminium. For steel, it's 200,000, give or take a bit. And the area equals 200 square millimeters. Okay. Now, if we're using consistent units, we have to watch your units here. If we use megapascals, square millimeters, and force in newtons, then we should get an extension in millimeters. So we'll get change in length. Whoops. Which member do you want to do?
That one, you did the 3.53.
Let's do this one.
Oh, okay.
Because it's 5 meters long, I don't have to work out the length. This one, okay?
Yep.
Change in length is going to be 7.5 kilonewtons, which is 7,500 newtons. It's all good. Times the area, 200? No, sorry. FL, times the length, which is 5,000 millimeters, divided by 69,000. Times the area, 200. Does anyone want to calculate that?
Yep.
2.71
Oh, no, that's the whole thing, yeah.
millimeters.
Yep.
Okay. So if we are building this truss out of 10 by 20 aluminium, that member there would get 2.7 millimeters longer. Okay. That member would get a bit shorter. You'd end up with a deflector shape. All right. That's what Jim's referred to as the 19th century method, and then you redraw it, either using elaborate cosine and sine of angles, or you just redraw it with AutoCAD or whatever you like. But that's the deflection of trusses. Okay. The energy method says that, you know that the formula for work is force times displacement. Okay. You've got a force, the deflection of the truss is your displacement. Therefore, work is done on that truss to make it deflect. And where does that work go? Where does the energy go? The energy goes into either the extension or the contraction of those members. So again, it's the force times the displacement in each of those members is going to equal the force times the displacement of the overall truss. So that's the foundation of the work method statement, the work way. It gets a lot more complicated, but that's basically what you're doing there. All right. I want to talk a little bit about the assumptions of this in real life. Let's start criticizing this truss. It's not symmetrical. Let's start criticizing it from the point of view of how is this not a realistic problem? Doesn't what?
Give you a width of the timber and then like that.
No, we've got a width. We've got aluminium members there.
You mean that you've got a roller on one side and a pin on the other?
You got a roller on one side and a pin on the other. Yeah, so what does a roller look like in real life?
It's not actually fixed to anything, and the truss needs to be fixed.
Oh, it's fixed enough. It's fixed to this side. Yeah. But you're right. What does a roller look like in real life? Have you ever actually seen a roller?
No.
There is one in a railway bridge in Sydney somewhere. But we use a notional roller for something which is not, hard fixed. But in reality, let's say there's a roof truss and it's sitting on the wall there. The wall can lean over a little bit, but it's not really a roller. Still, there's going to be some residual force being able to be applied there. And is this side really fixed? What does a fixed joint look like?
Welded joint.
No. What are you welding it to?
That's what I'm saying. That's why you can't do it with timber. So that's why.
Well, where didn't it sound aluminium?
It's actually got to be anchored onto the beam. Well, even that's not enough.
Even anchored, when you do your geotech stuff, you know that a ground anchor is a spring. It's not fixed. There's no such thing, really. There's no such thing as a fixed joint. If you push on anything hard enough, it's going to move. So there's no such thing as a fixed connection. It can be relatively fixed and very stiff in comparison to that, and that's good enough. But this is idealized to say that whatever's here is strong enough, so strong compared to that we can ignore it. And it's saying whatever is on this end is so flimsy that the force required to move it is so small compared to the truss that we can ignore it. But in reality, that's almost never the case. So when you do your structural analysis, think to yourself, what happens if this is not really a roller? Or what happens if this is not really fixed? All right, that's one thing. Let's go to the next assumption.
You wouldn't have those non-force, zero force members in there.
Why not? I've seen plenty of trusses like that.
Yeah, but why would you put a member in there if it wasn't doing anything?
Okay, how is it not doing anything?
There's no load on it at the moment, but if it was a roof, it would be the load. You'd be putting something right on the end of where that is.
So if I have a batten
in the corner, yeah, exactly.
If I have a batten right there,
Yep.
that's no longer a zero force member. Okay, so sorry.
The wings blowing on the roof, or you might have something.
Yeah, but say we have a roof, we put battens on it.
Yes.
Any comments yet?
I would just say one assumption we've made is that we're looking at it 2D and there's forces.
Yeah, there's three-dimensional forces. That's okay. Let's stick with 2D for a bit.
Like axial forces.
What about them?
Like,
Okay, I just drew a batten in the middle of the member there. Does anyone mind that?
No, because it's going now your truss is taking and bending, and you can only have an actual force on your member.
So if I load that up, I've just got a bending
Yep.
into there.
And that won't work.
Well, it will work. We do it every day.
Collapse.
No, it won't.
Straight away, as soon as you
No, it won't. It won't collapse. It just means that your analysis is based on a faulty assumption.
Yeah.
Your analysis says this only takes tension or compression, but I've just put bending in it. All right, so that bends from there to there, and everything else is fine.
No, that was still distorted.
Yeah.
And latch.
How would that distort anything else here?
It's just changed all your loadings on each member. by taking-
Sure, okay, there's going to be loading. The loadings, I put a load there, all the numbers change. Does anything else change?
Top one? Did that change? The 5? That would drag it out, no?
What about this member? Is that member? Sure, the axial force changes, but is it going to stay in axial force? It might go to tension, that's still an axial force.
But it's going to have a moment.
It's going to have a moment. Why would it have a moment?
Well, it's continuous.
That one from there to there?
Is it continuous?
No, they're not. Trust me.
No, if it's a pin jointed truss, there is definitely a pin there and a pin there
okay.
and there. But have you ever seen a truss with a pin joint like that where that's not a continuous member?
No.
They're pretty rare.
Still.
mostly you've got a big thing here, you've got a steel plate there, you've got bolts in here like this. And that's one major fixed joint. What I'm getting at is pin jointed trusses are fairly rare in the real world. Fixed trusses are much more common. So your timber truss in your roof, you know, with nail plates and stuff, that's not a pin jointed truss, that's a fixed truss.
Yeah, that's an issue I've come with doing mine.
So when if that's a continuous member, we put a load there, that's going to make that bend outwards like that too. And then that's going to make that bend down, bend up like that. So it just puts bending moments into the whole thing. What else is wrong with this? In terms of, we work out the deflection, we call it 3.5 millimeters. How do you know it's going to be 3.5 millimeters? All right, let's imagine this thing's made out of steel again, okay? And you come and make this joint. So you come and joint, you've got a piece there, you weld a hole in it, you have a piece coming here, the bolt goes through that hole as well, another piece comes here, and because you're a fabricator, you drill a 22mm hole there, you put a 20mm bolt in it. What happens? You make it so tight it doesn't move, that's called, yes, that would be a friction bolt, friction grip bolt, and that is exactly where I'm going, because when that pulls apart, you get the 2mm slip and the 2mm slip, and if we were only talking 2.7mm extension, we've just doubled or eliminated our deflection. So joint slip is significant in trusses. One way around that is, like you said, friction grip bolts. A normal bolt, you do up snug tight, and in theory, when there's a force on it, the pieces come apart and they bear between the hole and the bolt. And so there's the bolt, there's the hole, and that's pulling that way, the bolt pulls that way, there's your bearing area there. When you have a friction grip bolt, what you do is you say, we're going to tighten the bolts up really, really, really tight. And so you tighten them up by hand, and then you put a certain amount of extra torque in them. And that squashes these things together so much that they can't slip. And so you get rid of the joint slip that way. So your larger structures will have TF bolts, which is I have to look up what that means. But it's basically tightening them, doing them up really tight. You do have to watch out for that. It's a hole that'll come into the steel design later on. You've got to make sure the faces between the plates match and are prepared properly and all that. If you can avoid it, do basically. So having calculated deflection of trusses, it's all a load of nonsense in the real world. And the way you probably want to do it is, if I have it open here still. No, I think we lost it.
The question you have to do, there's three ways of doing it. The 19th century, the 20th century.
Yeah.
Okay, so what was the 20th century one?
The 20th century was, once you've worked out the lengths, drawing in AutoCAD, and just, draw the circles and arcs and stuff till it works out. Which really is still 20th century. 21st century is you do your, sorry, I can't work it from here. But I did a structural analysis on the problem in the text, and it just calculates the deflection. So you open up Space Gas or whatever structural analysis program you're using, put your truss in, put the loads in, there's your deflection. I guess what it comes down to is when you're at work and the engineer comes to you and says, can you model this structure for me, find out the deflection, pay attention to those conditions. Is that really a pin? Is that really a pin jointed thing, or is it continuous? Mostly when you model it up in Space Gas, it fixes everything, so you have this rigid truss. So you've got to make sure you know whether you're dealing with a pin jointed truss or a rigid truss, because it makes a big difference. So a little hint for life: when you design a portal frame like this, you typically do these as pin joints at the bottom, because you put a footing there. You've got to be really sure that your footing is not going to rotate in the ground. because just a little bit of rotation of the ground, and that'll start turning into a pin, basically. What I call shedding load, sheds load up to the top. So when you model it, you normally model it as a pin. But if you come and you're really close on the deflections, and it's like, do I make the beam another bit size bigger to get that extra less millimeter of deflection? You think, can I actually get any force into the ground, any bending moment into the ground there? And if you have a look at your foundations, you might be able to, and that'll fix your deflection problems.
If the post goes into the ground, can you use it as a fixture, or it's still a pin?
Oh, it depends.
Rather than a footing, the post sitting on the top, if the post goes in.
We're getting into steel design now, but when you bolt a column down, if your bolts are inside the flanges of the I-beam, it's normally notionally a pin, but it'll still take some moment. If you want to make it fixed, you've really got to put the bolts on the outside of the flanges of the beam, if you're going to put anything like the capacity of the beam into the ground. And if it's an independent footing, it's probably going to rotate on you, unless you really work hard to make sure it doesn't. If you are building a picnic shelter and you cast your post into the ground, yeah, you might be able to rely on that as a fixed connection, but bear in mind, as a fixed connection, it's going to rotate a little bit. So if you model that as a fixed connection, without pin there, without pin there, you get much less deflection. But then you should equally ask yourself, is that realistic? The true answer lies in between. It's not quite pinned, it's not quite fixed. Somewhere in between is the true answer. And so, bear that in mind when you design stuff. Does any of this help? Okay. Any more questions? Okay. The topic, the energy and unit forces might get you. If we need to talk about that again, we can do that. I can't do that right now because I have to go back and study it because I hate it as well.
I think that's where I might want to stay with this.
Yeah. Okay. Yeah, watch out for units. Using millimeters and megapascals and newtons helps a lot. But yes, everything comes in awkward units. Your velocities in furlongs per fortnight, and you've got to translate that down. There's a Murphy's law about that. Everything is in the least usable units. So, yeah, I remember my first year of engineering was basically working out how to translate units between things. And learning to think in millimeters instead of centimeters and all that stuff. And then you'll go somewhere and you'll have someone who throws stuff at you in feet and inches.